Good afternoon, everyone in India, and good morning, all those who are joined here. This is live stream. Greetings from Science and Technology Wing, Embassy of India, Moscow. National Science Day is celebrated in Russia on 8th February every year to mark the establishment of Russian Academy of Science on this day in February 1724. Similarly, National Science Day is celebrated to commemorate the discovery of Raman effect on this day in 1928 by the Nobel laureate Sir C.V. Raman. India celebrates National Science Day on the 28th of February every year. This coincidence of both the National Science Days in the month of February gives us an opportunity to have a joint celebration to mark these special days. And this special month, we have today two online expert talks from the noticed scientists from both the countries. May I now request the International Department of Russian Science Foundation, Russian Academy of Science, uh, Ms. Ina Serious, to introduce the Russian speaker for his welcome remarks.
Dear colleagues, ladies and gentlemen, I welcome you on behalf of the Department for International Cooperation of the Russian Academy of Sciences to a meeting devoted to Science Day in India and Russia. It gives me great pleasure to open the event with the introduction of the first speaker. I welcome the full member of the Russian Academy of Sciences, Director of the Institute of Archaeology, Vice President of the Russian Academy of Sciences, Nikolai Makarov. Nikolai Andreevich, you're welcome.
Dear Professor Das, dear Indian and Russian colleagues, good afternoon, good morning. I'm pleased to welcome the participants of the Scientific Russian-Indian meeting devoted to the National Day of Science of India, which will be celebrated on the 28th of February, and the Day of Russian Science that we marked on the 8th of February. Let me first inform those of the Russian audience who may be not known about the historical aspects of the National Science Day of India. On this day, in 1928, Indian scientist Sir Raman discovered the phenomenon of scattering of photons, which was later known as Raman effect. 2 years later, in 1930, he got the Nobel Prize for his remarkable discovery, and this was the first Nobel Prize for India in the field of science. To mark the discovery of his famous phenomenon, National Science Day is celebrated each year in India by the resolution of the Indian government starting from 1978. The 8th of February was also chosen not by chance to mark the day of Russian science. It was on this day in 1724 that Tsar Peter the Great signed a decree on the foundation of the Russian Academy of Science and Arts, as the Russian Academy of Sciences was called at that time. Russian-Indian scientific relations have long historical traditions. It is difficult to find the field of science that has not been seized by our corporations. Science was the whole complex of interaction between Russia and India, our friend, ally, and strategic partner, with whom we share common understanding of the role of cultural and civilizational values in the world development. At present, when bilateral political relations at all levels are actively developing, it seems advisable not only to revive, but also to improve Russian-Indian relations in the field of science. Using this opportunity, I would like to appeal to the participants of this meeting to encourage them to consider the possibility of organizing joint projects and conducting joint research with Indian experts in different fields of science in the interests of both sides. I am happy to congratulate our Indian colleagues on this remarkable day, and I wish all of you new discoveries and achievements. Let all your ambitious goals will be achieved and the greatest scientific projects will be successfully carried out. Thank you.
Thank you, sir. We have the
Thank
noted
you, Nizam. I love you.
scientist, Mr. Debashish Das, the director of RR CAT, who's from the 26th batch of BARC. He joined BRC in 1983. He's a Homi Bhabha awardee of BRC Training School in Electronics branch. Mr. Das has held responsible positions in BRC and other DA units. He has headed Electronics Division, BRC, during the period from January 2015 to October 2016, and subsequently as a distinguished scientist. He assumed the office of Associate Director, Electronics and Instrumentation. Mr. Das has held additional responsibility of the Chairman and Managing Director of Electronics Corporation of India Limited, Hyderabad, from November 2016 to June 2018. Mr. Das has been conferred with many DAE Excellent Group Achievement Awards and has been the recipient of DAE Special Contribution Award. Since 2019, he is leading the R&D activities of Raja Ramanna Center of Advanced Technology Indore as director. He has been in many scientific and technology development forums in various roles, including the Apex Committee member for various organizing moving exhibition on Indian contributions in mega science projects such as CERN, ITAR, FAIR, TMT, and many others. May I now invite you, sir, to give your welcome remarks.
Thank you, Dr. Sisir. Am I audible?
Yes, sir.
Okay, thank you. So, at the onset, on behalf of all Indian colleagues and participants, convey our heartiest congratulations to all Russian scientists, engineers, researchers, and students on the occasion of Russian Science Day and Indian National Science Day celebration through this online joint Russian-Indian meeting today. It's indeed a momentous occasion for India because we are aware that the Russian Science Day is celebrated every year on February 8 to commemorate the establishing of Russian Academy of Sciences in 1724, and the Indian National Science Day is celebrated every year on February 28 to commemorate the discovery of Raman effect in 1928. We express at the beginning our gratitude to Dr. Sisir Sotria, Counselor, Science and Technology, Embassy of India, Moscow, Russia, and his team for organizing this online celebration jointly with Russian Academy of Sciences. This joint meeting today will have experts from Russian Academy of Sciences and Raja Ramanna Center for Advanced Technology, a R&D unit of Department of Atomic Energy in India. They will be delivering their talks on laser, photonics, and particle accelerators. It is our proud privilege to also welcome Professor Nikolai Markov, and I heard him. I fully endorse his views that India has been an integral partner in the growth of science in both the countries and across the globe. And this is a very, very opportune moment that we have this interaction session or this meeting on this occasion. So it's my share of from all of us in India to welcome Professor of Russian Academy of Sciences and also the expert speaker who will be delivering the talk from RAS and all those Russian participants who are present in this meeting. I also take this opportunity to welcome all Indian delegates and colleagues participating in this meeting and the Indian speaker Mr. Purushottam Srivastava, my colleague, a senior scientist from the center. Rajaramanna Center for Advanced Technology, RRCAT, has intense R&D activities in the frontline science and technology areas of lasers and accelerators. I'm delighted that this meeting will further pave the way towards fostering the science and technological growth on either side through this meeting. Now, without taking much of the time for the meeting, we are all eagerly waiting to listen to the experts' talk from Russia and India. Of course, last but not the least, the support of Mr. Sergey Malenko and MS Inna in organizing this event is duly acknowledged. Thank you everyone.
Thank you very much, sir. May I request the representative from Russian Academy of Science, Ms. Enna, to kindly introduce Professor Andrei Naumov for his first talk.
Yes, thank you. I suggest that we now begin the next part of the program by listening to the lectures to be given by Russian and Indian scientists. And since the Russian researcher is the first to give a talk, may I introduce Professor Andrei Naumov. Andrei Naumov is a professor of the Russian Academy of Sciences, head of the department at the Institute for Spectroscopy of the Russian Academy of Sciences, head of chair at Moscow State Pedagogical University in Moscow, board member of the Quantum Electronics and Optics Division of the European Physical Society. So please, Professor Naumov, take the floor.
Good morning, good day, dear friends, and thank you very much for kind introduction. So, and now I'll try to share my screen. Okay. Okay. And full screen. Okay, everything is okay with my screen. Okay, I hear me.
Yes, you are audible.
So, okay, it's great pleasure to see all of you, and my best regards and congratulations both to Russian and Indian participants with this important days, Science Day in Russia, which we had a few weeks ago, and also National Science Day in India. So my talk has a close relation to the Raman effect, because Raman effect on single molecule is our dream. And in my lecture, in my talk, I'll speak about possibility to see single molecules and single nanostructures of different type. And it's very, very important part of photonics, of whole field of science, because now we start to prepare very powerful instruments for sensorics and nanodiagnostics of different materials. Actually, we can sense even single quantum effects, and also we can recognize single nano objects like virus or different bio objects. So everything is okay with my voice and with sound.
Yes, it's okay.
Yes, it's okay. So because I have not any any proof that everything is okay. So okay, let me start. single molecule spectroscopy and possibility to see single molecule optics and possibility to see single molecule has not too long story, only 30 years. As always with Nobel discovery, we had quite dramatic pioneer competitions on the board of 80s and 90s. You can see that two pioneer works. First one was done by group of Professor Mörner, who got the Nobel Prize 30 years later. It was first discovery of absorption of single molecule in solid. It was done at the end of 1989. And a few months later, a group of Professor Michel Larit, at that time he was professor in the University of Bordeaux in France, they succeed with measurements of fluorescent spectrum, luminescent spectrum of single molecule. These experiments were separated just by a few months. But you see the price is only one, and Professor W. Mörner got it in 2014. So, and you can see how this field grows up. At the first years, it was investigations of low temperature dynamics of doped condensed matter, where people used single molecule as a very effective spectral probe to sense structure and dynamics of condensed matter. At the end of 90s, people succeed with single molecule imaging because technology succeed with preparation of very sensitive CCD detectors, CCD matrix detectors. Then we can realize single molecule imaging. So, and you can see images of single molecule which are on the glass substrate or incorporated in some thin film. On the board of 90s and zeros, single molecule spectroscopy goes to room temperature, and people succeed with observation of single molecule at room temperatures. And you can understand that a huge community from life science also join single molecule spectroscopy community, because it's very, very powerful tool to study different processes for life science. And then you see a lot of new directions of these studies, because not only single molecule we can study, but also other single quantum objects, like semiconductor quantum dots, and also nanodiamonds with colored centers, and some kind of macromolecules, and many, many other quantum objects. And as a result, at the end of zeros, people succeed with realization of super resolution fluorescence microscopy, optical microscopy with resolution up to a few nanometers. And then we obtain the new instrument, fluorescence nanoscope. And this discovery was marked by a Nobel Prize in Chemistry in 2014. And now we have a strong applications of this instrument in different field of science. For example, single molecule cytometry. Now we can prepare some kind of biological analysis on the level of single molecule. Thus, we can solve a very interesting task for biophysics. Also, this story came to quantum optics, because single molecule is ideal source of non-classic light. Thus, we can use it for building of quantum computers and so on. So, of course, it's very interesting story for theranostics, when we use single nanoparticles, not only for nanodiagnostics of biological processes, but also for therapy of different diseases. And of course, our dream is some kind of on-chip single molecule spectroscopy, when we can put some spectrometer just on chip, on some on some consumer electronics like a smartwatch or smartphone and so on. And of course, here we should write one more direction of our research, single molecule Raman spectroscopy, because when we study not only luminescence spectrum, but a Raman spectrum, we can realize spectral analysis. So we can realize chemical analysis of any matter. So, and all the players of this game you can meet at a very famous international conference, Hall Burning and Single Molecule Spectroscopy, which was last time in Russia a few years ago, and now it will be organized in Germany 1 year later, and very welcome all the people to this important international meeting, because you can meet all the players of the single molecule spectroscopy field. So, and what is the problem? Problem is so-called diffractional limit in optics. It was discovered 100 years ago by German scientist Ernst Abbe. He found that when we use usual optical microscope, we are limited by so-called diffractional limit. Because of diffraction on optical element, we cannot resolve objects with sizes less than lambda divided by about 2. It means that when we use visible light, we are limited by values like a few hundreds of nanometers. It means that with conventional, with usual optical microscope, we cannot resolve very small objects, never, because this is principal limit of optics. For example, here you can see some neurons of brain of mice. And you see that you cannot resolve single neurons in such a sample, because you are limited by this Abbe diffraction limit, lambda divided by 2. Another situation exists, and another situation takes place when we consider point like light source, for example, single molecule. When size of light emitter is much smaller than light wavelengths. For example, size of single molecule is about 1 nanometer, and visible light is something about 500, 600 nanometers. So, and if we have such light emitters, this is luminescence emitter, for example, some dye molecule. So you can solve the this optical task of diffraction on optical elements in usual microscope, and you can calculate how what is the shape of image which you obtain with usual optical microscope. It's some kind of a student task, because this task can be solved mathematically, analytically. And you see how looks this image. This is ideal image of usual point like light source. You can see that it's some kind of two-dimensional Gauss function. So, and if you have such image, which you detect with a very sensitive CCD matrix detector, you can feed this image by two-dimensional Gauss. Then you can recalculate the position of point light source, namely this lateral position in the plane, focal plane of our optical microscope. And now, in this case, we are not limited by diffraction limit. We can recalculate the position with precision, which is limited by only signal-to-noise ratio. So, if we have bright dye molecule, we can detect the image of this dye molecule, and then we can find the position with very high accuracy. And you can see that if you collect something about a few thousands of photons from such kind of emitter, you can resolve the position with accuracy about 10 nanometers without any electronic microscope, without synchrotron radiation. You can recalculate, you can find the position of this molecule with accuracy up to a few nanometers. The best values which people achieve in experiments, it's a few angstrom. You can see in this paper, people succeed accuracy about 9 angstrom. And in our measurements, we achieve accuracy up to 5 angstrom. So, and of course, the question is how bright molecule is. And you know that now people from chemical science, they can synthesize very, very bright luminescent molecules. For example, this is usual rhodamine molecule. And if you have usual blue laser, you can achieve a very, very bright, luminescence. So, and even single molecule from such dye, it emit up to 10 to the 7, 10 to the 8 photons per second. So it means that we can achieve such a huge accuracy, such a very nice accuracy for very, very small exposure time. Of course, if we have not ideal point light source, for example, emitting dipole, we should take into account diagram of emission, because when we consider emitting dipole, we have a very very complicated shape of this image, so-called point spread function. But nevertheless, modern computers can recalculate these images too. So, and we can find not only position of our emitter, but also orientation of molecule in the space. So, but of course, in order to realize super resolution microscopy techniques, we should consider at least additional things. Namely, in order to reconstruct the sample nanostructure within diffraction limited volume, within a very, very small volume, less than lambda divided by 2, we need measure each label coordinates with nanometer accuracy. And also, we need to realize separate detection of each molecule, because if molecules emit light at the same time in far field with our usual optical microscope, we again obtain image which do not allow us to reconstruct the structure. We again limited by diffraction limit. So we need to separate emission from different label molecules inside of this diffraction limit. And of course, we need to realize quick automatic image processing and data analysis with modern computer, because in order to observe this nanostructure for large macroscopic sample, we should proceed the data for millions or even billions of label molecules. So we need a very powerful computer. This is the reason why this super resolution microscopy technique sometimes people call as digital microscopy, because in principle, in order to realize this technique, we need a powerful computer image processing. So, and how to do this? This idea came to the mind of a few scientists over the world, but the most successful was group of Professor Eric Betzig from United States, and they suggest to use effect of blinking of single molecule. Idea is the following: if we have some sample and we put some label luminescent molecules inside of this sample, we can realize the following effect. We can look on the molecules which emit light only in certain moments of the time. For example, we can switch on and switch off the luminescence by additional laser. And as a result, if we have a proper concentration of these labels, at each time moment, we will have in each diffractional limited volume only one emitting molecule. For example, like here, we have some sample, and we have a lot of label molecules, like here. By the way, do you see my mouse on the screen? Is it okay, or?
Yes, it's visible.
Yes, okay. We have a lot of label molecules around my sample, for example, 2 neurons. But of course, if I consider usual optical image with usual optical microscope, I will be limited by diffraction limit, and I cannot resolve thin, fine structure of my object. But if I have images, fluorescence images of different label molecules at different times, you see that in each frame, I have only a few molecules. Then I can measure, I can detect these images with my sensitive CCD matrix, collect this data in my computer, and then evaluate, realize the image processing, and find these coordinates of my emitters. And I can do it for many, many frames, which I measure at different time moments. And then I can realize computer rendering of my image. Then I obtain some digital image of my sample. And now I have not diffractional limit, because each coordinates for each label molecules, I reconstruct with nanometer precision. Thus, I can realize this thin structure of my object. Of course, again, I need some kind of very powerful computer image processing. I need a special software, special algorithm, and this is very actual topic in our science. By the way, as I know, in India we have a very strong programming school, and I think it will be a very interesting task for young scientists in India, because you know, there are a lot of special programming facilities now, and machine learning is one of the topical field of science now. So, and you can see example of how it looks like. This is very famous image from so-called storm techniques, stochastic optical reconstruction microscopy. You see, this is some biological objects, neurons of mice brain, and you see, with usual optical microscope, we are limited by diffraction limit, and I cannot resolve single axons. But now you see, we have a lot of label molecules around these neurons, which were linked by a special biochemical procedure. And we measure something about 1 million of label molecules here. And then we realize this computer image processing, like I told before. And you see now, I can reconstruct even single neuron and even single synapse. So, and I can study different processes, not only structure, but also processes. And a few more examples. For example, you know, now people consider very strong and very very difficult task concerning COVID pandemic, how virus goes inside of cell. And our technique allows to visualize this process, because we can put single label molecules on the virus and realize the tracking of single virus around the living cell. And you see, it was done many years ago, by the way, by a group of Professor Brochl in Germany. You see, this is living cell, and you can consider how a single virus goes inside of cell. And now you can understand what is the nature of process when virus goes inside of cell. And this is one more recent paper from our colleagues from United States of America. They consider the drug discovery inside of living cell. You see single drug molecules which goes inside of living cells. This is membrane of living cell, and you can consider even single drug molecule which goes to living cell. So, and what I would like to say now, we have a very powerful instrument for study of different processes in many fields of science. This is example of biological physics and medical physics and life science. But topic of research of my group is little bit another, but of course close to this instrumentation. We try to use super resolution fluorescence microscopy for material science, as well as for nanotechnologies and quantum technologies. And of course, we have a deal with single molecules, different single molecules, macromolecular machine, and so on. Now we work not only with single molecule, but also with semiconductor nanocrystals, so-called quantum dots, and I will show you a few examples later. We use this labeling single molecules for nanodiagnostics of condensed matter. And for example, for microrefractometry of thin films, for reconstruction of different material characteristics of solid films. This is one more very topical field of research, spectroscopy of nano and micro diamonds with colored centers, because such kind of objects is very very useful for single cell thermometry or for quantum optics tasks. One of our last work concern perovskites. It's a very interesting material for modern solar energy technologies, because we can realize very cost-effective material for modern photovoltaics, and we try to use the super resolution fluorescence microscopy to understand structure and dynamical processes relaxation in such kind of material. And I would like to pay a special attention for our Indian colleagues on our last work on Raman spectroscopy. As I told, our dream is a realization of Raman spectroscopy on single molecule. And we can do this when we use special metasurfaces, some plasmonic metallic metasurfaces, in order to increase the efficiency of Raman spectroscopy in many, many times. It's so-called surface enhancement Raman spectroscopy, and we also try to do this work. But as concern our first goal, we try to use each single molecule is very effective spectral nanospy in order to understand what happens in local nanometer surrounding of molecule. And the idea is the following. The optical spectrum of a single molecule, of some dye molecule, which we put inside of transparent solid, this spectrum is very, very sensitive to local surrounding, because pure electronic transition in such molecule, it depends on the state of electronic shell of molecule. And as a result, this spectrum is very sensitive to the state of local surrounding. Then we can use this single molecule as a single nanospy to understand what is it. And it is very interesting that at low temperatures, we can measure this very, very narrow spectrum, which correspond to the pure electronic transition in such a molecule. Thus, we can do the following. Of course, there is a very difficult and strong and extended physics around this phenomenon, because we need proper theories to describe temperature and temporal dependence of parameters of such spectrum, because each molecule interact with local surrounding, and we need a proper theories to describe this interaction. For example, here you can see what is interaction of single molecule with tunneling transition in local surrounding. You see that we can even visualize single quantum effect. We can investigate it not only in theory now, but also we can test it in experiment, because if we have such tunneling system close to our dye molecule, and we measure repeatedly luminescence spectrum for such a molecule, such tunneling transition we will see as a jumps of our spectrum. Then we can visualize this luminescence trail, the spectral trail in time, and we can see this jumps, and we can directly sense this quantum transition. So we have a very, very sensitive quantum sensor. And of course, if we have proper theory, we can reconstruct many parameters of these processes. Not only tunneling system, but also we can study electron-phonon coupling, we can study so-called parcel effects, and many, many others. So, for example, you can see how we can use single molecule is very, very sensitive temperature nanosensor. We can take a single molecule and we can consider temporal behavior of this spectrum at different temperatures. And you can see, for example, at temperatures 4 or 5 Kelvin, we see some splitting of our spectrum. It means that close to our, that we have some tunneling transition close to our molecule. Thus, we have splitting of spectrum because of very, very fast jump of spectrum between two positions. When we increase the temperature, let's see from 4 to 6 and 7 Kelvin, some another tunneling system activate, because we have higher temperature and we can activate transition either through higher barrier. Then we have a splitting between another two positions, not only between these two positions, but also another one. It means that we have activation of another tunneling system. Then when we increase the temperature, we increase the jumping rate in this tunneling system. So by analyzing of these jumps, we can understand the temperature. So we have a very, very temperature sensor with a size less than 1 nanometer. So we can put such a extremely small temperature sensor to everywhere, to condensed matter, to living cell, and so on. And we can reconstruct the temperature. We can find the temperature in very small volume for different objects. Also, along the whole temperature range, you can observe spectral peaks broadening and shift because of electron-phonon coupling. So we can study vibrational excitation in our sample. So, but what is very important, we can do not only single molecule spectroscopy, not only spectroscopy for one molecule, but also for many molecules. But now we don't need to realize blinking of our labels, because you see we have a strong distribution of this spectrum along the spectral range. So if we have a tunable narrowband laser, for example, dye laser, and we tune the laser excitation wavelengths, we can excite different molecules separately in different diffraction limited volume. So, and we automatically solve the problem of recognition of a lot of label molecules. You see the values in homogeneous width of our spectrum divided to homogeneous width for single molecule can achieve the values 10 to the 5, 10 to the 6. It means that I can reconstruct such a huge number of molecules within each diffract limited volume. And the idea of experiment is very simple. This is my sample. It's a thin polymer film. It's about 50 to 50 micrometers. And I put inside of this film a lot of dye label molecules. And then I scan the laser excitation wavelengths. Let's see, from blue to red. And you see when the laser is in resonance with the electronic transition of certain molecule, this molecule emit light. Then with computer, I collect all the data and I can reconstruct not only position of this molecule, but also its spectrum. So it means that actually I can issue some kind of spectral passport for each of molecule in my macroscopic sample. For example, I can realize some kind of far-field nanodiagnostics. You see, I have a thin film, polycrystalline film. It's frozen orthodiclorbenzene, some chemical structure. And I scan my laser, and I detect images and spectra for about 300 of thousands of single label molecules. It's so-called Terylene molecules. Then I realize image processing for each of molecule, and I find the spectrum. And now I can realize so-called multicolor diagnostics of my sample, because I can visualize, for example, here you see, this is shape of crack in this part of my film. And you see, in usual white light microscope, of course, I'm limited by a diffraction limit. I cannot reconstruct the shape of crack. You see here, it's just 1 and 1.8 micrometer. But if I reconstruct spatial density of my label molecules, I'm now not limited by diffraction limit, because for each label molecule, I reconstruct the positions with nanometer accuracy, so I can recalculate the shape of crack, of this defect in my sample. And this is very interesting for material science, because now I can study structure on sub-micrometer scale, and I can understand how what is the life of different defects and cracks in some perspective materials, in some functional materials. So, of course, I can realize some kind of spectral nanotomography, because I can visualize only molecule with certain frequencies, with certain color. So, and the situation is about like in astrophysics. A few hundreds of years ago, the famous astrophysicist William Herschel, he studied Milky Way by recalculating all stars in the sky. You see, this is picture from his writing book. He put the position of each star on the sky, and when he analyzed the spatial distribution of the stars on the sky, he got the knowledge about forming and structure of our galactic. Now we have about the same situation with in solid state physics, because for our macroscopic sample, we can find many positions of label molecules, and they are colorized because of different spectrum. And now we can get knowledge about forming and structure of my solid sample. Could you please say me how much time I have?
You have 10 more minutes.
10 minutes. Okay, thank you very much. So I will be quick. So of course I can expand the approach. I can measure not only position of spectrum of molecule and spectrum, of molecule, but I can measure dependencies of single molecule spectrum on various external parameters like laser power, temperature, external fields. Then if I have appropriate theories, I can find different material characteristics, some kind of effective macroscopic characteristics. And then I can map the distribution of these parameters inside of sample and look for different correlations. For example, I can realize polarization mapping. For each molecule, I can find the orientation of this molecule in the space. And then I can see how my label molecules are oriented in the sample. I can realize some kind of vibrational microscopy, because for each molecule, I can measure temperature dependence. And when I analyze this temperature dependence of spectrum, I can find the energy of vibration in my solid film. And then I can map these vibrational parameters in the space. So I can find some kind of hot spot in my sample and cold spot, because on the sub-micrometer scale, I can find a very strong fluctuation of different parameters. And I know everything about properties of my sample, even in sub-micrometer scale. So, for example, recently we realized some very specific technique for microrefractometry, because it's very important to understand what we have with material characteristics on sub-micrometer scale. You see, this is some molecular crystal, frozen hexadecane, and we put about a few thousands of label molecules inside of this sample. And we find the parameters, spectral parameters of these molecules, depending on the temperature, on the laser excitation power. Then we can recalculate the spectral parameters to the effective refractive index value. Then we can map the distribution, this effective refractive index value within our sample. And we can do this on the sub-micrometer level. And this is very important, because if you try to construct some kind of nano device, you know that it's very topical now, because we think about electronic and optoelectronic device in our consumer electronics. So we need to realize some optoelectronics on the chip. So we should understand what happens with material characteristics on sub-micrometer scale, because you can use usual polymer and you will have a strong distribution of parameters on the sub-micrometer scale. And if we consider Raman spectroscopy, it's very interesting that in addition with different things, we can also find the chemical structure of our molecule, because we can realize idea of Raman fingerprint. And many thanks to Indian researchers, and especially to Nobel Prize winner Raman, who discovered these fields. You know that in about the same time in Russia, in Soviet Union, we also have excellent researchers, Professor Landsberg and Professor Mandelstam, who also study this effect. And in Russian science, we called it combinational scattering of the light. And you see, this Raman fingerprint allows to recognize the chemical structure, because we have a specific spectral peaks. And when we consider Raman spectrum from single molecule, and we enhance the scattering by specific metal surface, we can reconstruct the chemical structure of analyte. And it is very interesting for such field of science like macromolecular machines. For example, recently we start collaboration with corresponding member of Russian Academy of Science, Professor Yulia Gorbunova, and we try to study such a very complicated molecules, so-called molecular nanomachines. For example, this is so-called single molecule magnet, and this is molecular switching molecule, switch molecule, and so on. And now we have a possibility to look on the inter and intramolecular processes on the very, very small level of single molecule. And as I told, we can work not only with single molecule, but also with other nanostructures. For example, semiconductor core shell nanocrystals, some kind of colloidal nanocrystals, so-called quantum dots. They have a very high quantum yield, broadband absorption, they are very photostable, and so on. And you know that people already use such kind of materials, for example, for light-emitting diodes, for television, for new generation of television screen, and also for solar cell, in order to realize cost-effective and very effective photovoltaic cell. But of course, in order to construct such devices, we should understand what happens with quantum dots on the level of single quantum dots. And we can do this. You see, this is a picture from our recent measurements. We excite quantum dots, which are located on the glass substrate, with a laser, with a continuous wave laser. And you see the effect of so-called blinking behavior. You see that these bright single quantum dots, they stochastically jump between bright and dark state. So, and of course, if we try to use such quantum dots for any applications, we should understand the nature of this very intriguing behavior. At the same time, we can reconstruct the position of each quantum dots with huge accuracy, up to a few nanometers. The same idea like previously with single molecule. And we can measure some temporal behavior and the relaxation behavior and so on. For example, in our recent work, we study effect of spectral diffusion. We observed that single quantum dot at room temperature, it stochastically changes the color because of different processes inside of single quantum dot. For example, if we have some kind of defect, we can observe some relaxation of the defect, like jumps of spectrum of single quantum dot. And we can do this and find some spectral spatial relations and so on. And of course, we can do this in 3 dimensions. Our very good friend, Professor Mörner, he suggested idea to transform point spread function by using of adaptive optics elements, so-called special light modulator. If we calculate specific phase mask, we can transform usual point spread function, usual instrumental function, this Airy function, to specific 2 lobes picture. And the orientation of this 2 lobes picture here depends on the depth of our point light source in relation to focal plane of microscope. Then we can reconstruct not only lateral position of our sample, but also third coordinate, again with nanometer accuracy. Of course, again, we have a very difficult computer task because we need to calculate the specific phase mask. And we do this with our collaborators from Lebedev Physical Institute. This is a branch in Samara in Russia. And they calculated very effective phase mask, which allows to transform this instrumental function for single emitter. And you see how it looks like. Now we can recalculate positions of each label molecules in all 3 dimensions. So we obtain 3-dimensional nanoscopy, and this is a multicolor nanoscopy because for each single label, we measure also spectrum. And now we can use this instrument, for example, for visualization of different processes. For example, if we realize tracking of single molecule, we can try to understand filtration of different nano objects inside of porous materials, and we did it recently in this work. So, and I'm going to my conclusion. This is one of our laboratories, and you see it's quite complicated setup. But our dream goes to on chip and try to realize all this equipment in very, very small devices. And we work on all this field with single molecule, with quantum dots. We study dynamics of complex solids like glasses, polymers, nanocomposites, and many other things. This is our group, and we collaborate with many institutions. Our very good friends from University of Bayreuth, Professor Jürgen Köhler and Professor Lothar Kader, both of them, they worked with Nobel Prize winner W.E. Mörner, and Lothar Kader, he was even co-author of pioneer work in 1989, and also our friends from Australia, Belarus, and from different cities of Novosibirsk, and our group and the people from different universities over the Moscow and Russia, from of course my chair from Moscow State Pedagogical University, from Moscow Institute of Physics and Technology, Moscow State University, and Skoltech University, high economic schools, and so on. And of course we acknowledge support from different foundations, and we very hope that we can add in near future our friends from India, because there are a lot of strong scientific groups in your great country. So, and a few words about my chair in Moscow State Pedagogical University. You can see, by the way, academician Gregory Landsberg, who also participated strongly in the study of Raman scattering effect, and Nobel Prize winner Igor Tam. He was a professor of our chair many years ago. Our teachers, Professor Shpolsky and Professor Personov, and our honor professor W.E. Mörner and Michel Arid, who got this name, honor professor of our university a few years ago. So, and I would like to pay some attention to our unique educational bachelor program, Fundamental Physics in English, which we realize in collaboration with Russian Academy of Science, and very welcome foreign students, especially from India. We would be grateful to see our friends at this interesting bachelor program, because you can study fundamental physics in English in our university. And finally, one more thing, it's about our international journal, Photonics Russia, and related international exhibition, Photonics, World of Lasers and Optics. And I think if you pay attention to the journal and to this exhibition, you can find many interesting things in optics and spectroscopy, and the applications in different fields of science, not only material science and physics, but also medicine and biology and many other things. So this is key directions of further development. Extremely sensitive spectral nanoprobes for the study inter and intermolecular processes, physical chemical properties of matter on the smallest level of single molecules, super resolution microscopy, and of course impressive innovative potential applications. Sensors, including Raman sensors, with cytometry, thermometry, magnetometry, chemical analysis, fast and cheap optical DNA sequencing, drug delivery, phototherapy, theranostics, controllable non-classic light sources for quantum optics, nanoelectronics and photonics, and of course on-chip technologies. Thank you very much for your attention.
Well, I would like to congratulate Professor Nauma on his excellent presentation. Thank you very much. And I will call upon Dr. Shrotia.
Thank you very much, Professor Nauma, for such a wonderful presentation and covering the single molecule spectroscopy and the various applications. I think the last slide which you listed would be so important to the researchers, and so many use cases and in innovation can be developed. There are no questions on the chat box, but there will be many questions by the experts who are joined here. So may I request our RRCAT team to put it?
Yeah, I'm Das here. It's I would like to congratulate on behalf of all my colleagues by a very interesting topic of single molecule spectroscopy studies that he has done on a diverse and variety of things. And it's been really very enriching for me because I don't come from this field, but I really appreciate that. I had few, query, I mean, just inquisitiveness that you see, has there been anything definite done in biophotonics? Because let's say we have to study the skin depth signature of biological tissues. That was one query. If there is some specific studies have been done, and extending the same topic, I would like to Professor Andre to respond whether this has a potential in security parlance in the terms of still in a large crowd, the identification of certain entities who may be present in the crowd is still based on imaging through lights. So whether this technique in a very specialized way can find some way in this. So I would like to Professor Andy to respond on these two.
Thank you very much for excellent question. You are right. We have a potential for such kind of study because, as you see, if we have a proper sample preparation, we can understand what exists in our sample on the level of single molecule. And as I told, I think the main idea we should use not only luminescence but also Raman spectrum. Because if we put our sample, for example, for biophysical purposes, we have some complicated molecules which we want to recognize. If we know Raman signature, so we can reconstruct this data and we can understand that we have a certain macromolecule or some molecular complex in our sample. The same situation with security. If I know Raman signature for some molecule or macromolecule or molecular complex or some nano objects, I can reconstruct this. So, and you are right, we can do this, and this is a very, very topical and very interesting story. So I think this is way where we should go. So thank you for question.
Thank you. Thank you. Just I would like to share that actually in our center also we have a small group which works on the biophotonics, and we have come out with a very, very cost-effective product which can detect the presence of a cancer molecule in the oral cavities. Just creating a Raman spectrum. So that's already in use, but we wanted to know whether we can do a skin depth analysis signature. That's very useful.
So thank you. Maybe we will find some joint points.
Yes. Thank you. Thank you so much.
Thank you.
Yes.
Thank you.
Some of the joint possibilities will be covered by the next speaker also, and I'm delighted to introduce him. Mr. Purushottam Srivastava is an outstanding scientist and director, Proton Accelerator Group, Raja Ramana Center for Advanced Technology, Department of Atomic Energy, Indore. Mr. Srivastava started his initial career as microwave and RF engineer with design and development of solid-state amplifiers for the first Indian national satellite INSAT-2A at the Space Application Center, ISRO. Mr. Srivastava later joined RRCAT Indore and was involved in the design development of high-power RF microwave systems, advanced high-voltage solid-state pulse modulator, and crucial components including electron guns, solid-state amplifiers for particle accelerators. He significantly contributed in setting up and commissioning of various particle accelerators at RRCAT and at Mangalore University. He has contributed in setting up and commissioning of the first Indian infrared free electron laser, IRFEL, which is for irradiation applications built by RRCAT. He spearheaded R&D test and supply of crucial high technology components for Large Hadron Collider LINAC 4 and Compact Linear Collider CLIC test facility at CERN, Switzerland. He has won 11 Department of Energy prestigious group achievement awards, including 2 as the team leader for his contribution at CERN projects. He has served as an expert in various national and international committees. He has served in the Scientific Advisory Board of International Particle Accelerator Conference, IPAC, and later as organizing committee member of IPAC. As technical coordinator, he has spearheaded the high technology contributions to various international accelerator projects like Large Hadron Collider at CERN, Switzerland, and presently contributing to R&D phase of upcoming Proton Improvement Program PIP2 project at Fermilab, USA. He has also been making effort to bring this SNT awareness among students, teachers, and public at large through various vibrant outreach programs. This is one where he's promoting science, and he's running summer courses at Particle Accelerator, laser, and related science and technologies at various institutes. This would interest him that the last speaker also had an academic program for the students, which was flashed in the last slides. So I request Professor Srivastava to integrate the two efforts together and bring out some joint programs for the benefit of the researchers and the students. Professor Srivastava has deeply interacted and he's got various deep links in R&D labs and various agencies in Russia. He's published over 180 publications in peer-reviewed national and international conferences, journals, and workshops. May I now request Mr. Srivastava to kindly present and give his second talk for the day.
Well, thank you, Dr. Chaudhary. And it's my, am I audible, please? So
yes,
it's my privilege because after listening to such a nice and beautiful talk, then I would like to cover some of the things on the how, because you are driving us, science drives us, and then to come up to the level what you expect. So I will try to cover some of the aspects on science and technology on accelerators and lasers, which is the task given to me. And I'm thankful to Mr. Devashish Das, who has tasked me for this work. This is an international outreach towards bringing up together the scientists and students and researchers. So would like to also thank Inna, who has done all the Miss Inna, who has done all the efforts towards coordinating and sending the details. I would like to now share and let me know if it's okay. So I hope you are able to see my slides.
Yes, it's come.
So first of all, let me thank Nikolai Makarov and Andrei, as well as Sergey and you, and to bring me here and then have giving me a chance to come up for the awareness of science and how it drives the technology. And my talk is actually Kant Twarak or laser, Vigyan or Praudhyogiki ke Drishtikon, that is a particle accelerators and laser, science and technology perspectives. So with that, I say Dobry Din and Namaste from India to all the participants and speakers. And congratulations from India on the occasion of Russian Science Day. And I am presenting it on behalf of my big team from all the groups and divisions and sections here, who have contributed, and they are the experts, and I'm just only a presenter here on behalf of RRCAT. So, okay. So we started somewhere in 84 when the new center was identified for accelerators and lasers by Department of Atomic Energy. We are a constituent unit of Department of Atomic Energy, Government of India. And it was earlier named as Center for Advanced Technology. Now the name itself suggests advanced. So of course we have to, it is a big challenge for all of the people here, and they come up to the level which is expectation from the government and the researchers. And then this was the foundation day, February 19, 1984. And this shows the Center for Advanced Technology. And it was later on renamed because Dr. Raja Ramanna played a key role in setting up this center and selecting Indore as the site because he was the driving force in doing all that. So we remember, and it was then renamed as Raja Ramanna Center for Advanced Technology by then Prime Minister of India, Dr. Manmohan Singh. And later on, in when we celebrated DA's Diamond Jubilee, we have changed it as a common logo. So, Rashtra ki seva mein Parmanu, that is atoms in the service of the nation. So we just completed 37 years on February 19 this year. Now, this is the thing which drives us, serving mankind through photons from accelerators and lasers. Now, everywhere you have electrons, and how you use them becomes the technology or the driving force in different type of devices. Like we just listened from previous speaker, a great job done by them. So when electrons are accelerated to high energies by means of accelerating them through electric fields by various means, then what happens when they are passed through a media or a bending magnet? When they pass through a bending magnet, they generate electromagnetic radiation in the form of synchrotron radiation, and which is taken through beam lines for various scientific applications. And I will try to cover some of the things which is striking science which is coming out of these applications, these beam lines. And then, of course, when you go for the medium energy electrons, you are very well know that when you bombard it on materials of high Z materials, and you use X-rays in the form of Bemstern, so that photons we use for irradiation, sterilization, as well as for preserving the food for long. And you know that, and I understand that Russia has done a great sort of job on this application, particularly BINP and also NIFA. Then of course, another thing on the photons is the light amplification by stimulated emission of radiation through various mechanisms and media, forming various type of lasers. And the type of media you use and type of techniques you use gives you different lasers, and it has got different science coming out of it. And what some of the things we have already seen, and what Mr. Debashish Das also just mentioned, I will try to cover some part on those societal things also, which has come out of the photonics applications. So I will try to first go on the electron accelerators and the science which is done through the use of these accelerators, which was initially the thing which we started. So we started with first, I recall the great interactions earlier between the colleagues from India and Russia, like was already mentioned. And we started from microtron, building a microtron indigenously. And then I can mention here that the components, whatever you see, except few of them, were all designed, developed, tested, and deployed in our machines by Indian scientists and engineers, and they go hand in hand. And then we go for the booster, which increases the energy from 20 MeV to 450 MeV or 550 MeV, depending on which machine you want to inject it into. For example, Indus 1, I'm showing a picture of Indus 1 here with 4 magnets and then the RF cavity sitting here. Now, as I mentioned in the earlier slide, that the accelerating field is now here is RF. And then we go up to 450 MeV, and then it becomes the storage ring. So you have 6 beam lines coming out of it, and striking science has come out of this. Some of things I will try to cover, including some of the things done for the space program. and that is very important to mention here. Then the beam at higher energy, once you fill up Indus 1, is taken to Indus 2. And I tried to show some magnets. The red things are the magnets, and the bending magnets. Then you have the photons coming out, I mean the synchrotron radiation source. So we have got 17 beam lines already operational. What you green you see are all the operational things, and then coming up in future. So this is the Indus 2 machine, which is 2.5 GeV, 200 milliampere, and we have 3 insertion devices in that. And I will try to show some of the important things on that part also, if time permits. And what you see here on the top is the building, which is Indus 1 and Indus 2 buildings are next together. And I will try to show a top picture also. And on the left side, you see the Indus 2 ring. So the magnets and then the cooling systems and the you see the vacuum system, and just on the last behind, you see the RF fed into. And very important to mention that we had, I mean, the team here had come up to the challenge to make 70 kilowatt class solid state amplifiers at 505 megahertz, and also now the circulators. And this was a big challenge. So this is what I was telling, the science drives the technology, and it becomes very important to meet the expectations. And these are the 4 cavities we are using. So now we have connected and one more cavity we have installed. So not going into much details. Now on the science side, we have this beam size 200 micron to 50 micron, horizontal and vertical. And you can see that 1.7 million revolutions. Just for the students, I tell this in the ring. And then a vacuum of -10. So we have a very high capable ultra high vacuum technology group along with the physics behind the vacuum. And then we have the large number of subsystems which have gone into making this, and a large number of engineers who have realized this dream of science in a stipulated time, which government has mentioned. And then we have the different type of subsystems like vacuum, magnets, power supplies, controls, diagnostics, and many things with the support of Indian industries. And they are one of the best class in India. So, and on the right side below, you see a beam line area where researchers are gathering and doing the experiments. And you see the hutch here where the beam line is coming. So I will try to go, as I told you, this is the top view. You see the Indus 2 building from top. And then this is the part which is coming from the injector, and then Indus 1, I mean the booster inside here. So this is the part which is coming as the transport line 3, which connects booster to Indus 2. And what you see here for the students, and particularly for the younger people who have joined, I would like to mention that this was a striking sort of science here coming out of the this thing. The ring circulates the electrons at 2.5 GeV, having the vacuum inside. And what you see blue, these are the magnets here, and the beam lines are coming out and then taken out. And these are the shielded walls. So everything is safe outside, and still we have the hatches. So it comes out in a very, well planned manner. So this is the Indus 2 building, 172 meter in circumference. Now this shows, I will take you inside as a virtual tour, if you would have been here. So these are the beam lines you see here going out, magnets. These are the vacuum systems, quadrupole systems. Then the beam line coming out of the shielding wall. Then what is coming here? These are the 2 beam lines again coming out. And then you have the undulator here first. So this way I am taking you on a virtual tour inside the tunnel. Of course, the machine was off when I made the shooting here. You would like to understand that. And then the third undulator. And what comes at the last is the RF systems. You see here. Yeah, these are the magnets again. And these are the RF systems which are coming fed through the coaxial lines to the cavity. So now for the younger students, I would like to create awareness on the beam lines, what I was mentioning. So you have these electrons passing through the bending magnet and then emits radiation in the form of synchrotron radiation in the bending magnets. And it depends on the energy and the magnetic field. You can have X-rays and soft X-rays for useful for proving the structure of materials. And this brings the science in front here, like X-ray diffraction. The broadband radiation is passed through a monochromator and the desired wavelength is selected. So you can select also and do the desired science out of it. Now, all the optical elements used for this purpose together constitute a beamline, as I mentioned. And a synchrotron source has several beamlines, as I also mentioned in my photograph. And this is another one. This is the insertion device. You can put a undulator where you have periodic magnetic field of alternatively reversing polarity designed to make the electron trajectory wiggle. So you call it as a wiggler and generate intense synchrotron radiation. And this way you can increase the intensity and tune the synchrotron radiation to higher frequencies. So a smaller wavelength. These are the things which I mentioned, the science coming out of this machine. So beamlines on, you can see each subject here is a very specialized subject where people keep using 140, institutes from all over India and bringing out more than 780 users and more than 900 in one of the time. On the engineering applications, then we have soft X-ray reflectivity beamline, soft and deep X-ray lithography beamline, angle resolved PES beamline, position emission tomography, angle dispersive X-ray diffraction beamline. Then we have microprobe X-ray. So what I would like to say that those who are actually interested, they can go to each one details. And these are the different beamlines set up by different institutes. Like you see Saha Institute of Nuclear Physics. Then you have UGC DAE CSR beamline here in Indore. Then RRCAT beamlines and again BRC beamlines on Indus One. So if people are interested, they can come to our website and we have an online system where you can apply for a beamline, of course. So you come here, you see the beam, I have given the website here on the bottom and you can come and search and then each one you can find out. Suppose I click the first one, you get a better detail like this. So you can learn what science you can do out of this and you can match with your requirement to what you want to do over here. So this way you can see, select the students and the researchers select all over India, and then they can come and continue.
Raja Ramanna Center
Now
for
I will tell
Advanced
you something
Technology,
about
a
the
constituent
beamlines.
unit of DAE, has India's only two synchrotron radiation sources, Indus 1 and Indus 2. When a moving high-energy electron is bent by a magnetic field, it emits radiation called synchrotron radiation, which is used for experiments in experimental stations called beamlines. The beamlines are national facilities dedicated to the utilization of X-rays for the study of materials. There are 17 operational beamlines on Indus 2 and 6 on Indus 1 today. The various beamlines at Indus 2 and the associated experiments are as follows: X-ray diffraction measurements for structure determination at the angle dispersive XRD and the extreme conditions XRD beamlines. Hard and soft X-ray absorption spectroscopy for structure and chemical state determination, X-ray imaging, protein structure determination, X-ray fluorescence spectroscopy for the determination of chemical composition and trace elements, for soft X-ray reflectivity for the study of thin films. Hard X-ray reflectivity studies, small angle X-ray scattering, X-ray lithography for making high aspect ratio structures, X-ray photoelectron spectroscopy for determination of the electronic structure of materials, and analysis of stress, strain and microstructure in engineering components. Experiments for Mangalyaan and Chandrayaan 1 and 2 missions for the calibration of detectors and validation of software have been carried out. Determination of the crystal structures of materials for understanding and enhancing their properties are carried out. Proteins present in all living organisms have extremely complicated structures which can be easily determined at a synchrotron beamline. Uranium-based nuclear fuel have been studied, which is important for fuel production and reprocessing. Detailed measurements and analysis have confirmed the non-toxicity of mercury-containing Ayurveda medicine Ras Sindura. X-ray lenses developed at Indus have been used for in-house applications and at the Diamond Light Source, UK. Imaging of the internal structure of tissues and human bones have been carried out. To further enhance the properties of synchrotron radiation at Indus 2, 3 insertion devices have been commissioned. 2 devices U1 and U2 are designed to deliver plain polarized radiation in the deep ultraviolet and soft X-RE region, and the device U3 is designed to deliver circularly polarized radiation in the soft X-ray region. The related angle resolved photoelectron spectroscopy beamline on U2 is now in operation. The total number of user experiments have been increasing steadily.
You got muted. Kindly unmute. By accidentally, I think you got muted. Please unmute yourself.
Okay, okay. But you were able to listen to the video sound. It's fine.
Yes, yes.
Good, good. So now I come back to the presentation mode. So this is what I was trying to say, that this is an sort of thing which we have updated. Of course, you can see the still the papers had been published and 179 in 2020 because work from home. Yes, but on the because of the COVID, there was an effect on coming users, and most of the things were done. Samples were coming still, and we were still doing. Machines were running when the lockdown was, I mean, opened. I mean, unlocked period. So you see 930 to 345 has come down, but anyway, that itself is a good number of signs which coming out of the machines. So these things which already I have shown in the things which has been shared by my colleagues on the various ISRO projects. So I need not go into details of this because this has already been shown in the video. And this is one of the important scientific investigations done using industrial beam lines on the protein crystallography as a very high resolution microscopy, which enables to see at atomic resolution beyond the capabilities of powerful light microscopes. So this is what our colleagues have done and the users have used, and there are publications coming out of this. And of course, as was the thing on the Ayurveda, studies by Ministry of Ayush, Government of India. So some of the chemical impurities in some homeopathic medicines which were of interest of Ministry of Ayush were analyzed using X-ray fluorescence technique. So it leaves a lot of opportunity of scientific investigations to come forward and then relate it back. These are another thing which I would like to now coming from synchrotron radiation. I'm now coming on the lower energy machines, and this shows a 10 MeV LINAC which we have commissioned at very close to agricultural market, and we ultimately plan to go for the agricultural irradiation. So this is right now a 6 kilowatt beam line, I mean beam power machine which we have made at Araket, and I recollect a lot of interactions with NIFA. NIFA, St. Petersburg. And then we have done some medical devices sterilized at the facility once we have got the approvals, and we have gone ahead with the sterilization, and we are continuously into making progress in this field. Now I'm coming on the proton accelerators. Well, of course, we have made this shows some of the our preliminary physics design because this is what initially the center when it was conceptualized we were tasked to make on the spallation research, and we have started looking after maturing because we were told, and I recall Dr. Bawalkar and Dr. P.D. Gupta, who were very keen on the science, and of course Dr. V.C. Sani, our earlier directors, and Dr. Nayak, and now Mr. Debashish Das, who had been keen on the scientific investigations. And this is what the spallation research for the material science research is what we may we would like to investigate further, and we are making efforts on that. And you can see the paper on from my colleague Dr. Vinit in NIM. So I will not go into details of this, but this shows now we have, as I mentioned here, this shows an architecture where you start from an ion source and increase the energy of the H minus particles to using initially warm accelerators, and then we are having partnership with Fermilab to learn on the SARF technologies on different class of different types of resonators, superconducting resonators, right from spoke to low beta, then high beta, and learning from that, we would like to go for a high intensity superconducting proton accelerator program in pulse mode at RRK. So we are making a modest initiative on that, and this shows the facility setup because ultimately to go for this scientific investigation in material science. So that's what we have set up and learned from these technologies, from forming the cavities, electron beam welding, and then going to multi-cell. Like initially we made 9-cell 1.3 gigahertz, and later on to 5-cell. And our colleagues here have done a lot of efforts in learning and adopting and this technology. And then we could get a lot of success now on the different characteristics of the superconducting cavities. And this shows one of the cavity which has gone after a lot of reiterations to 21 million volt per meter acceleration in the vertical test stand, where we test these cavities at 2K, and we have a dedicated cryogenics team. And next I have to take it to after the bare cavity tests, we have to take it for the dressing of the helium vessel over it. So this has been also done, and then we have put it into horizontal test stand, where test at high power level, because vertical test stand tests at a low power level, and horizontal test stand tests at high power. And because it's horizontal, it's called horizontal test station. And another thing, after the learning from Indus 2, this is another 40 kilowatt amplifier, 650 megahertz, which our RF people have made in-house for the energizing this, and this will be a contribution to PIP2 program also in a large number. And BRC colleagues have made this LLRF and RFPI for the STS, and which will also set up a direction for evolving further pulsed RF LLRF systems in future. And now, another thing, learning from all this, we have gone one step ahead, and I'm really very happy to share the latest result, which has taken us to 28 million volt per meter with a satisfactory Q value, and we got testimonials from the experts from Fermilab. Yes, we have crossed that bar. Of course, there are some issues that we are addressing, which you already know, that there are always challenges when you step by step when you go up. So those challenges we are meeting and then trying to mitigate. Now, from electron accelerator, now the electron accelerator can drive a laser also, and that is the future now. So you can see the compact accelerators. Of course, we have to go a long way, but this is the modest beginning, and we started with IRFEL here, and just since we have accelerators and lasers both sitting here, so there is a marriage between the two, and we are fortunate to have this marriage, and then come out the accelerator of 22 MeV drives an undulator, and then we, with the help of mirror 1 and mirror 2, you see here, we come out with output radiation in 12 to 50 micron, which is itself is aimed for a different type of scientific applications. So we are now building the beam lines using this. So this shows the first lasing in India using this free electron laser. So you see the accelerator here, 22 MeV from the gun. It is a high quality electron beam, comes taken through the undulator magnets and goes, undulates, and then comes out, and then you have the radiation, which is now in the oscillator configuration, and you get the infrared laser out of it. And this shows the complete technology behind this science. I mean, to bring this science up, expectations of science up. So this shows the complete tunnel where we have the accelerator here, and then the undulator is sitting at the far end. And these are the results which I have been shared by my colleagues of IRFEL who are doing this for the first time. When we got it, the lasing we got at 28 micron at 24 MeV, and the peak current was 50 ampere, and the peak power of 4 megawatt. You can calculate from the pulse width and then the things which are. And this shows on this right is the real laser power, which has seen as 7 milliwatt average. So we have to update this to further values, and this shows that transverse laser mode profiles shown here. So we have the perspectives in future that to increase the CW average power to 125 millivolt, and then augmentation of operating wavelength to 75 to 100 microns, and design of a terahertz FEL. And you know, there's exciting science coming out of terahertz, and a lot of good applications, like one which already similar to what Mr. Debashish Das was asking, and the experiments to use the FEL optical beam for materials research. So this drives the material science also here. So this was the date when we got the first lasing, and it was an encouraging moment for all of us. Yes, we can take it ahead. And then now we are carrying out beamline. Beam lines for users for carrying out experiments is in progress. Now coming to the lasers, thanks to the laser team who has shared, and I will show some of the things which have been done here. So what you see on the right first is the laser cutting using NDR, and this is for the younger people who are participating here. Yes, there is an application coming out from the NDR. So this is the thing which I would like to put forward, that yes, our team at RRK, the laser people here have developed the NDR lasers of different power levels with 250 watt average and 5 kilowatt peak, and 500 watt average and 10 kilowatt peak. And then of course, ceramic reflector based 1.5 kilowatt average power pulse NDR laser. So these are for the different applications which we are aiming for using them. And of course, 40 watt and nanosecond pulse diode pump green lasers for pumping of dye lasers. and 20-watt average power fiber laser marker system. This is very important application. And all fiber 100-watt of TM doped CW fiber laser at eye-safe wavelength of 1940 nanometer for potential medical applications in lithotripsy. So this is the one thing which actually the center is actually giving back to society on the medical and societal applications. And this is what we have to look forward. And as from the last speaker also, we learned a lot of potential for that. So I look forward on those aspects for association here. So these are the photographs you see of different lasers developed at RRCAT, and I have already shown you the video. So going to the next.
RRCAT developed a 2 kilowatt fiber laser-based LAM system and being deployed for making complex engineering components for various applications.
So, okay, thanks for the music from the team. Nice thing out of a boring talk. So, okay, so this is the laser additive manufacturing coming out of the laser science, and then different applications, and we have got a lot of applications which I cannot list everything on here. But this is something which I invite the younger people and I mean the younger researchers to come forward, and they can come forward with novel ideas to bring up this science out of these different type of lasers. And now what we are coming up, what Mr. Das was mentioning, this is one of the onco-diagnoscope where we have made some progress, and this laser biomedical instrumentation developed by our teams here has got a lot of appreciation from and they are much in need. So these are the photonics technology based compact standalone and field usable instruments which have been developed considering the societal healthcare requirements in India. And this is a very handy equipment and has already been carried at many places. So this is a oncodiagnoscope is an optical spectroscopy based point of care device for non-invasive screening of oral cavity cancer. And we heard about it in the beginning. Yeah, and this is used at different hospitals, including Tata Memorial Hospital, Mumbai, and various cancer screening camps in Madhya Pradesh on over 2,500 patients. That's it itself is quite a good number. And the accuracy of diagnosis, which has been taken out of the data, is more than 90%. So, of course, there are challenges. The technology has been transferred to the industry, as well as the device is also fabricated by our undertaking, that is DAE undertaking, Electronics Corporation of India Limited, Hyderabad, through technology absorption. And the units of the instruments are deployed for large-scale multi-center clinical validation. That is most important. And on the other side, we have the Raman probe, where photonics technologies for societal applications. Another thing is there. So Raman probe is a handheld optomechanical module for in situ measurement of Raman spectra from low Raman active materials like biological tissues. These yields artifact pre-Raman spectra, unlike the commercial probes, which introduce spurious spectra features in the acquired signal that interfere with the Raman signatures, appearing in the fingerprint region of 400 to 1800 per centimeter of the Raman spectra, thereby limiting the utility of the Raman spectroscopy systems. So this is capable of collecting good quality in situ Raman spectra within a few seconds of acquisition time from low Raman active materials like biological tissues. And the technology has also been transferred to Indian industry. Now I come to international collaborations, and this is the part which is what when we learn something indigenously, then you become I mean capable of partnering with the and that makes your progress faster. Like this interaction is making a lot of things to learn for the Indian young researchers and students, and this shows what this mega science, different mega science. This is an artistic picture made by an artist learning from the scientists, and these are the different time zones where these different projects are aiming at. You see the Big Bang, Sun is working on the Large Hadron Collider. Then you have neutrino, even earlier to that, elusive particle, and then the FAIR. Then as you progress in the formation of universe, you have the SK, which can probe into this time directions, and then 30-meter telescope, it has got its directions in this region, and then ITER, which works on the formation of sun. I mean, you're creating a sun almost in, and then LIGO, the most important one, where distant gravitational waves, an exciting science, which is coming out of black holes and merging stars far away, and then it comes and you are able to detect the minuscule signature of these gravitational waves by the LIGO project. And again, it's a beautiful laser which has to be built for it, and then the formation of these things, of course, you know this. And these are the different things I have tried to archive here: the CERN, FAIR, INO, ITER, LIGO, SK, TMT, and one more thing is MASS, which is missing here. This is the Indian partnership on different types of projects here. You can see on the Large Hadron Collider, I would like to mention something on FAIR. A lot of things have been contributed from RRCAT and ECIL, and then we are going for the INO, LIGO, and ITER, and then you see the SK and TMT. And here you see the contributions to CERN Large Hadron Collider, and what you see here are the magnets which are positioned here, and these magnets were the first to go in the tunnel, and these were supplied by RRCAT with the help of Indian industries like IGTR and Avsarala, Bangalore, IGTR in Indore. And then the dipole magnets started coming, and they started coming from a place where our 100 engineers and scientists had been deputed to test these dipole magnets and superconducting region. And these are the supplies from RRCAT, I mean from different industries through RRCAT, Electronics Corporation of India, then Kirloskar, and these are the things from IGTR. These are the JACs which have gone. And we became an associate member, a state of large, I mean CERN Council. I wrongly written LSC here. It's a CERN Council in January 16, 2017. And this shows what I was mentioning. All these dipole magnets were actually characterized by Indian scientists and engineers who had gathered there. And you see here our former President of India, His Excellency President Abdul Kalam Sahab, who had visited, and he was very much excited, rather, we were rather excited. Each one of us were excited to interact with him. And these are the post LHC recommissioning era, where we had sent teams for the cryogenics and the quench heater power protection supplies, all made in India and supplied to CERN. And this further beyond LHC, we now started partnering with CERN on the various aspects of LINEC 4, which is a new injector to increase the luminosity of Large Hadron Collider. And what you see is the LINEC 4 tunnel, and where Indian couplers, high power couplers, are sitting here. And of course, it's a small number, but yes, it gives a lot of learning when you are able to supply to such a large project and learn. And then we get in as a feedback, we got a lot of learning on the high power systems and RF systems, CW Klystons. And this is the modulator which was made in India and designed, developed, and made in India and supplied to test these cavities at CERN, LINEC 4. Now, on the last part, it is important to connect, as Dr. Shrotri was also mentioning in the beginning. So whatever science we do here, and then unless we connect our students and younger people, so they are the future. And each one of you who are listening here are important for us. And definitely you can make a difference. So this is the SNT awareness to students. And we run very vibrant programs and invite students. And this year we are inviting online on 28th of February, the students to join us and have interactions with our thing. And this shows some of the glimpse of the students. So this shows the orientation course which we are running here on accelerators and lasers. So we have very, dynamic and very enthusiastic partnership from all the gurus who are actually gurus, the teachers who are actually imparting education to all these 40 students from all over India, who come from almost 12 to 16 states of India. They join us, and then they get certificate after they, and we don't just leave them just like that, because then we ask them to perform on cultural programs, and then we ask them to come forward with seminars so that they become a real professional and prepared for the professional career in future. This shows the certificate, and you can see Mr. Debashish Das, our director here, and our former chairman, Mr. Sinha, who had Dr. R.K. Sinha, who had all the way come from Mumbai to encourage. And this is the student who is getting, one of the students. And of course, when we make these efforts, it is noticed by the people around, and then they come and visit, including the police and defense people. They want to learn, and this is the exhibitions we take moving exhibition we take to different schools and colleges and different type of international science festivals and science congress. And yes, when you do a lot of, devoted thing, like this, my devoted team here won best science exhibition award. And when we and it was the Mr. Debashish Das idea to put questions to the students and ask them, and they interacted. Like you can see here on the left side bottom, the students are solving puzzles, whatever they have seen on the laptop, and then we reward them with gifts and certificates. Now, coming to my last slide is the future perspectives. So, of course, we have made a modest beginning, and there are a lot of things to be done. Because I remember my seniors telling me that these are the toy machines you are playing with, and you have a bigger challenges in future. So, opportunities exist for close cooperation in particle accelerators and lasers, and related applications, including societal benefits and medicine, particularly. And this is what I look forward. Components for the particle accelerators and lasers and materials. So we can look forward on this. And these are some of the very important immediate requirement on multi-beam Klystron, circulators, niobium materials, ferrites, and of course, international collaboration for high brightness, low emittance synchrotron radiation sources. So we would like to learn from the already expertise available, and accelerators for societal applications. And I would like to put on record their contributions from all the groups of RRCAT and all the group directors and the division heads and section heads who had been very keen to share all the knowledge, and they are listening here. And contributions from various individuals is greatly acknowledged. So with that, I would like to end my talk. Thanks a lot. So I say dhanyavad and as possible to my Russian friends, and thank you.
Thank you very much, Professor Purushottam Srivastava. Are there any questions? Yes, please.
Thank you very much. It's a very, very interesting and excellent lecture. Thank you very much. I have two questions. First is quite concrete. Maybe I miss the information. You show some slide with a compact spectrometer for cancer diagnostics.
Oncodiagnostic.
And oral, yeah. What is the principle of this spectrometer? Is it luminescence or Raman scattering or some other principle?
So I would request Mr. Debashish Das to interact with you on this.
Well, I can only share whatever I have learned from my colleague. Is that it's not a optical, it's a Raman spectroscopy, because it uses a, I think, 632 nanometers wavelength, and then it shines. That's how we are able to get, it is a category 1 cancer. I mean, it's just as a very primitive stage where we have no other alternative to take biopsy and then find out whether there is a beginning of any cancerous cell. So this is a very handy tool, and it is based on spectroscopy.
Okay. Is it already commercial device or
yes,
just experiment?
Yes, no, it's not an experiment. Actually, as you have also indicated, actually the strength behind making this possible is a very strong predictive machine algorithm, adaptive machine learning algorithm, because there are a lot of artifacts, and to have a level of confidence, which is now our colleagues have reached greater than 90% of detection. And this is obviously requires a very large samples. So as we have seen that we have gathered samples close to 3,000 samples, and we have learned this algorithm, and that's how now it is 90%, and it's a commercial product available as a technology, and there are commercial companies who are selling this.
Okay, thank you very much. And the second question about about facilities of your electron accelerator. Was I right understood that you have a fully equipped laboratory for fluorescence microscopy? Yes, close to this beam, you have fully equipped, and people from other cities and even other countries can collaborate with you in order to make some experiments with samples. just in your facilities. Okay.
So
Yeah, I
fantastic.
will just, if I'll add to just a second, is that you see we have synchrotron radiation source which is at 2.5 GeV, and we are
Mhm.
pulling out the synchrotron radiation and different ranges of energies, which are
Mhm.
EV range to maximum about, if I'm correct, 25 keV range, and we have all sorts of experimental setup, which facilitate certain different type of experimenter. So this
Mhm.
facility is open to all, and we have around 800 to 900 experiments per year being done, and we have a very high impact factor publications coming to the tune of 130, 150 each year. So it's open. Yes.
Thank you. Thank you once again for very nice talk. Thank you.
Yes.
Thank you once again to all the audience who are listening, and especially the researchers and students. The Beamline application facility should be utilized, and you can give your experimentation, uh, targeted experiment on online also, and get in touch with Professor Purushottam Srivastava and his team. Also, there are lots of other facilities here in Russia where collaborative effort could be very good. And there is close to Moscow, there is one institute, JNIR Dubna, and there also linear cyclic particle accelerators are there, and many other fields of interest which Professor Purushottam talked about. Uh, I'm now there to thank everyone from my side and Embassy of India side, uh, to all the speakers and all the organizers, especially academician Nikolai Makarov, who joined us in the beginning, uh, Dr. Devashish Das, Director RRCAT. We were also supposed to be joined by Professor Bhavalkar, who's ex-director RRCAT, and he is not well today. He's down with spondylitis, and we pray for his early recovery. He's also the guru and teacher of Mr. Srivastava, and we would be, if you are hearing us, sir, we would be delighted to have your expert talk sometime and share your experience of collaborative efforts with India and Russia together. I also want to thank Professor Andrei Naumov for his brilliant presentation, and the integrated presentation was so interesting that you could not even blink an eye. I was supposed to be looking at the questions on the chat box on YouTube and FB, and I was not able to turn around and see what are the comments because of your brilliant presentation, and especially the use cases which your last slide was so much interesting for the future innovations. And I'm sure all our researchers are listening, and they will reach out to you to get going in that direction. We have many other institutes which are working in the area which you mentioned, and this live talk would later be recorded, is being recorded, and that will be given to them for further collaborative effort with you. Also, the interesting course which you mentioned, there are similar synergies with RRCAT and other institutes in India, and with Russian Academy of Science. We would like our researchers to come for these courses to you, and also Russian researchers coming to India and utilizing our facilities and undertaking some of the courses. So thank you very much, Professor Andrei Naumov. Indeed, it was an excellent, befitting tribute to Sir C.V. Raman, on whose Raman Spectroscopy and his the idea of single molecule spectroscopy, which you mentioned, and the uses to take it forward. Also, Professor Purushottam Srivastava, I thank you, and RRCAT team, Director RRCAT sir, and all the other team members for integrating this piece together from all sides and making a brilliant presentation. The videos of the extensive facilities which have not been seen by many were a delight to see live, and they've been recorded. And I'm sure so many researchers will find so much interest in these facilities, and especially the option which you gave to them of applying and using these facilities by applying online and coming up with their targeted application, and then thereafter seeing their results. So thank you very much. Also to the Russian Academy of Science team, Inna and Daria. Daria is the head of the International Cooperation Division. She works under Mr. Sergei Malenko. And I give the last word to Daria for complimenting the teams and the message from Russian Academy of Science. Thank you very much.
Thank you very much, Dr. Shishir, and thank you very much, all participants. Of course, first and foremost, I would like to use this opportunity to congratulate our Indian colleagues on the National Day of Science and wish them success in implementing their great ideas and plans. I wish these talented and hardworking people persistence in achieving goals, and of course, good luck. It happens to be important for scientists. One of the most significant tasks behind our department, the Department of International Cooperation at the Russian Academy of Sciences, is restoring and developing cooperation in different fields of science between our countries. I should say that in this, there is enthusiasm from both sides. During the last months of last year, 2020, we organized Russian-Indian joint scientific webinars on a very wide range of topics. They ranged from cyber-physical systems, artificial intelligence, quantum technologies, agriculture, food technologies, mechanisms of adaptation to climate change, ecology, material sciences, nanotechnology, and several more. Around 80 Russian and around 80 Indian experts presented their work and shared information about current research. We still expect large numbers of speakers to join our webinars and online conferences in 2021. Speaking of 2021, the schedule of topics for this year has already been agreed by both sides, and the first webinar to take place will be on the 10th and 11th of March. With our Indian colleagues, we will be discussing waste-to-wealth technologies. The relevance of this topic means it promises to be a very interesting event. We expect new methods, new ways, and new technologies of recycling and usage of recycled waste to be presented by the Russian and Indian experts. Once again, thank you very much for participating in this event. A separate thank you to our presenters today for very interesting talks. I'm sure the audience found them very interesting. And of course, thank you to the organizers. Dr. Shishir, thank you very much to the Indian side, to the Indian Embassy for participating in this. I look forward to our future meetings.
Thank you, Daria. I also want to just compliment and thank the Backstage, Vigyan Prasar, the India Science TV channel, and Dr. Kapil Tripathi, Dr. Venkateshwaran, and Mr. Somnath and their team. Thank you very much, Backstage, for bringing it live and seamlessly integrating it together. Thank you all.
I think, may I say 2 words?
Please.
I think I will express our common opinion if I say that we are grateful to Dr. Shishir Shropshia, the Chancellor of the Embassy in Moscow, Indian Embassy in Moscow, for his initiative to mark Science Day jointly, since both countries celebrate their Day of Science in February. So it was a good idea, Dr. Shishir, Dr. Shropshia. Thank you very much.
Thank you. Thank you, sir. Thank you to
Okay, thank you.
Have a wonderful celebration on the 28th. And we also take this opportunity live to congratulate you on the Foundation Day, which was a few days back, the 37th Foundation. Thank you very much.
Thank you. It was a very good interaction. We'll look forward to many more such fruitful interactions in future. Thank you so much.
Thank you very much. Thank you for nice